This is Jack Jackson. In this video we're going to be looking at the quotient rule. So we want to take the derivative of a quotient. A quotient, of course, is the answer to a division problem. So here we have one function f of x for the numerator, another one for the denominator, g of x. We want to find the derivative of that. Turns out the answer is you get the bottom function, g of x, times the derivative of the top, minus the top function times the derivative of the bottom over the bottom squared. Now, most of the time when we've been deriving these formulas for shortcuts, we've had to go back to the definition of the derivative and work from there. But here, since we already know how to do power functions and we already know how to do the chain rule, we're going to apply those rules to help us with this. And of course, we know the product rule. So basically, the quotient rule can be thought of as a product, and here's how we do that. So here's our derivation, or our proof of the quotient rule. So f of x divided by g of x can be thought of as f of x times g of x to the negative 1. Now this negative 1 out here is not an inverse function, it is really a power negative 1. So that's the reciprocal of g of x times f of x. That's what we have originally. Now we can think of this as the product of two things, so we can apply the product rule, which says it's the first, f of x, times the derivative of this second part, plus the second part, g to the negative 1, times the derivative of the first. Derivative of f of x, of course, is just f prime. Now here we have g inverse. So that's the derivative of g. Well, it's g to the negative 1. So it's negative 1 g to the negative 2, then times the derivative of the g. So I use the chain rule. So it's like you've done a substitution, u to the negative 1, where u is g, or the same thing. So g to the negative 1 power, the derivative is negative 1, g to the negative 2. So I'm applying the power rule, but notice the g and the x are not the same letter, so I still have to multiply by the derivative of the g. That's the chain rule. Okay, now let's just clean it up a bit. We've got the derivative now once we get the g prime here. G to the negative 2 is 1 over g squared. And then this is g to the negative 1, that's 1 over g. So I'm going to put this together in one fraction. That's f times g prime times negative 1 over g squared. The second one is f prime over g. Now I want to get a common denominator, so the second fraction I multiply by g of x over g of x to get g times f prime over g squared. And so the bottom then is g of x squared. And the top, if we put the one that's not a minus first, we get g of x times f prime of x minus f of x times g prime of x over g squared. And if it helps you to remember it, the g's kind of go on the outside here. The bottom kind of stays down the bottom there, and you square it. And then you have the bottom times the derivative of the top minus the top times the derivative of the bottom. Just like I normally write the product rule, the stuff that doesn't change I write first, then the derivative. There are some other orders here, although not as many as you might have in the product rule, because the subtraction doesn't commute. So we need this term after the subtraction. We need the subtraction on the one that has the top times the derivative of the bottom. And the bottom times the derivative of the top does not have the subtract or the negative in front. You could write this as f prime g if we'd rather, and g prime f if we wanted, but I like to write it this way. And some people will remember it this way. This may be a little fun little rule that might help you remember this. So if you say d is take the derivative of d high over ho, high on the top, ho on the bottom, is ho d high minus high d ho over ho ho. Bottom times derivative of the top minus top times derivative of the bottom over ho ho. Ho d high minus high d ho over ho ho. I have a colleague who actually sings this rule to the Snow White and the Seven Dwarfs song, Hi Ho. I'll spare you that, me singing, but there we go. Hi ho. Derivative of high over ho is ho d high minus high d ho over ho ho. So let's look at it how that works in an example. So here we have an example, 3x squared plus 2x minus 4 over 5x minus 7. So we want to take that derivative, we can use the quotient rule. So it's the bottom, 5x minus 7, times the derivative of the top, there it is, minus the top, that's this quadratic, times the derivative of the bottom over the bottom square. So you can see this. I always write that out so you can see exactly what we did in terms of the quotient rule. Next, we actually take these derivatives, the derivative of this, so the 5x minus 7 stays there. The derivative of this quadratic is 2 times 3 is 6. The power goes down to 1. 2 times x, the derivative is just 2, and the derivative of the negative 4 is 0, so this becomes 6x plus 2 for that derivative of that quadratic. And the derivative of this linear, of course, is just 5. Now we're going to clean up a little bit by multiplying out. We'll multiply these first two out with FOIL. 5x times 6x is 30x squared. Negative 7 times 2 is negative 14. For the inner product, I get negative 42x, and the outer product, I get 10x. That's added together to be negative 32x. Here I'm going to take the 5 and the negative 1, so negative 5 and distribute makes it negative 15x squared minus 10x plus 20. Now I'm going to combine like terms in the top. 30x squared minus 15x squared is 15x squared. Negative 32x minus 10x is negative 42x. And negative 14 plus 20 is 6. And it's still over 5x minus 7. And then if I can, I will factor the top. Looks like I can get a common factor of 3 out. 3 times 5x squared minus 14x plus 2, and then divide that by 5x minus 7. And the top doesn't factor anymore if we only allow integer coefficients, or even rational coefficients. It probably does factor, well, it definitely does factor over the complex numbers. So here's one for you to try. Why don't you try this one? Press pause, try this one, and then come back and we'll work it out. The derivative of 4x squared plus 7x minus 3 over 6x minus 4. Press pause now. Now hopefully you actually did this yourself. Let's go ahead and you can watch me work this out here. So we get a fraction. In the bottom we've got the original bottom squared. Now what do we have? In the top we have the bottom times the derivative of the top minus the top times the derivative of the bottom part. And it's over the bottom square. So that's correct now. I think we got all the parts there. That's from the quotient rule. Now what we do is we actually do these derivatives. So now this derivative is going to go away because I'm going to do that part. And we get 8x to the first power plus the 7, and then that part disappears. And this part, when we take the derivative, we just get 6 because that's a linear. So we have the answer now, but let's clean it up. So the first part I'm going to do right here, I'm going to do FOIL. 6x times 8x is 48x squared. Let's do the last term next. Negative 4 times 7 is negative 28. And the middle term, let's see. 6x times 7x is 42x. And the other one's 8 times 4 is negative 30. So we got negative 32x there. So you might do that in your head. This is actually 10x. Then I'll distribute the minus 6 here. And let's see what we get here. So we're multiplying all these by negative 6. That was a positive 4. Now negative 6 times that is negative 24x squared. Negative 6 times positive 7 is negative 42, and that's times our x. And negative 6 times negative 3 is positive 18. Now combine like terms in the top. 48x squared minus 24x squared is 24x squared. So we put that together. Negative 42 plus 10 is negative 32x. So that gives us our x term. And negative 28 plus 18 is negative 10. And there's our answer. Again, a little cleaner. Let's see if we can do any factoring with this because it started factored. Looks like I can factor out a 2 in the top. and then 24 divided by 2 is 12. 32 divided by 2 is 16, and 10 divided by 2 is 5. And then we would see if that factors any more. Let's see what we could do. 12x squared minus 16x minus 5, wasn't it? Yeah. So to get the FOIL to work, it's 12x and 1x, or 6x and 2x, or 3x and 4x are the possibilities, and then you get 1 and 5, 1 plus, 1 minus. Okay, so we just have to start trying these. I put a 1 here and a 5 here. That's 60 and 1. That's not going to subtract and get 6. Put the 5 here and the 1 here. That's going to be 5 and 12. It's close, but not quite 16, so that doesn't work. Try the 1 here and the 5 here. That's 2 and 30. That doesn't work. 5 here and 1 here. That's 10 and 6. Ooh, that would work if the signs were the same, but the signs have to be the opposite. So, no good there. 5 here and 1 here. That's 20 and 3. That's not going to subtract, right? 1 here and 5 here. That's 4 and 15. No, the difference there is 11. So we eliminate all the possibilities. So this one will not factor anymore, at least not with whole number or with the integer coefficients. So, or even rational coefficients. So unless we want to resort to using the quadratic formula, we're not going to be able to factor this anymore. So let's just leave it like that. So that is our final answer right here. Okay, that is the quotient rule in action. Next video, we'll be talking about the inverse function rule and use that to help us find a derivative of a logarithm.